EMF. That means where we had to move the magnet or the coil. There had to be a relative motion between the magnet and coil to induce electric current.
Sir, am I audible?
Yes, now you are audible.
Oh, yeah, yes.
In the electromagnetic induction, we had seen different methods of inducing electricity. The very first method we had seen was the motional EMF. Motional EMF, that means by creating a relative motion between the coil and the magnet, we generate
Yes.
electricity. We call it as motional EMF. Then we had seen by varying magnetic flux. So varying magnetic flux can be done either by just by changing the magnetic flux. It's not necessary to have a motion. We have some other methods like how to there the only condition is that there should be a change of magnetic flux. Okay, if there is a change of magnetic field lines which are crossing, then there will be an EMF induced in the coil. So these were the two methods. Today we will see about the alternating currents. What is alternating current?
Good evening, sir.
Yeah, good evening. So sorry for starting late. Let's see. Now today's topic is alternating current, AC. So how do we define AC or alternating currents? Yes, we define alternating current or AC current as the current. This is the current which changes its polarity. Okay, it
Yes.
changes its polarity. So the AC current or alternating current is the current in which it is the current in which the direction of current changes continuously. Current changes continuously. So generally in India, the direction of current changes 100 times a second. So that's a 50 cycles. So in India, the cycle of current is 50 cycles. Current changes
Yes.
continuously. Direction of current changes continuously. So how the AC current is represented? See, if we can represent the AC current as a function of EMF and time. We can represent EMF as a function of time, or we can represent current as a function of time. Like this. So we can give a sine curve like this. Okay. So we can draw a sine curve here. Let's say if you have function f of x equals to, if I draw here sine x. So Thank you, Shashi and Dhananjay for being maintained here. See, see what happens. We have seen, you can see here, I have drawn a curve of y equals to f of x equals to sine x. So in this graph, and you can see here, we can see the graph is like this moving up and down. Okay. So in this way, uh, okay. As you can see, this is the graph between y equals to sine x. So this is how an alternating current can be drawn as a varying EMF with respect to time. So suppose here on the time axis or on the x-axis, it is like this. We have taken on the time axis here. Here we have taken time, and on the y-axis we have plotted the EMF. So here this is the EMF. We found this as E naught. The maximum value of the EMF is called as E naught. So this value represents your E naught or maximum value of the voltage. You can see the direction or the amount of the EMF is changing. It is a varying EMF. So initially when we are at zero, the EMF is zero, then the EMF increases. That means the voltage increases. The voltage reaches the maximum. Again, the voltage decreases, the voltage falls to zero, and then the direction of voltage changes. The voltage now reverses in direction, it becomes negative. So here we find that the direction of voltage becomes negative. Okay. So here we can see that in this graph, you can see this is a graph. So in this graph, it is a sine function. So alternating current can be represented by a sine function or even a cosine function, where the EMF changes with time as a function of sine or as a sine function. It can also, we can also represent the EMF as a cosine function. So currently, maybe you are not getting the complete thing what we are discussing, but our topic is that the AC current, in the AC current, the direction of EMF is changing. Direction of EMF changes, and its frequency in India is 50 hertz. Now, why we use AC? Why should we use AC and why not DC? Why in India everywhere we are transporting electric currents in the form of AC currents, and why we are not using the DC current as the source? Because see, when you have to charge up your mobile, you have to use a charger. You have to convert your AC into DC. When you have to use your laptop, so then also you have to convert your AC to DC. So everything we are our fans are working on based on AC, but why can't we work on DC? Can anyone suggest a reason why can we not use DC for power transmission? Whatever power is transmitted, can we use DC current for power transmission?
No, sir. No.
We
No.
cannot, sir.
Why we cannot?
Sir, DC current is only unidirectional.
So what happened? So what are the losses that we will have? Is there any loss?
The current gets lost because it cannot travel longer distance.
Okay, see, the very first reason that in AC current we find skinning effect. I will tell you what the skinning effect is. So AC current shows skinning effect. That is, this current travels on this current it travels mainly on the upper surface of the wire, not inside the wire. Whereas about the DC current travels through the wires. Wherever you observe DC current, you will be observing that we can use thick wires. But for AC currents, we generally use a number of wires which are twisted together. We do not use a single piece of wire. For AC current, we use a number of wires which are twisted together that creates an that's easy for the transport of AC current. Okay. So,
Also, sir, DC current cannot travel very much long distances, sir, which AC current can do.
so why it cannot travel? The reason why DC current cannot travel.
No ideas.
No idea. The reason being that in the DC current, the current travels through the thickness of wire, and hence the heating effect generated with the DC current will be too large. The
Okay.
amount of
It
the amount of heat that will be generated through the wire, it will be too large, and hence the wire will start melting. So that is why it's not easy to transport DC current. Their losses will increase. So if you transport through DC, losses are more. There are
yes.
more losses in DC current. Also, there are certain devices which will not work on DC current. For example, you will have a device inductor which will not work on the DC current. So transformer and various other devices, they will not work on DC current. It's not easy for the DC current to step down or step up. That means decreasing the voltage of DC and increasing the voltage of DC, it's not too easy. Whereas for the AC current, we put up transformers to step down or step up the voltages. For example, from the power sources, wherever the electricity is generated, over there we generate electricity at 33 kilovolt. 33 kilovolt means you use 33,000 volts. This is the AC which is generated. So then after that it is transported to major cities where this is brought down to 11 kilovolt or 11,000. So from 11 kilo, this is a substation where they are brought down. After 11 kV, they are transported to other smaller units and brought down at 440 volts. After 440, they are transported to homes at 220 volts. So AC current can be transmitted at high voltages, but DC current cannot be transmitted through high voltages. So this will be a drawback with the DC current. Now, a number of devices are there. For example, you will have your inductor. Inductor means the induction cooker that you are using that will not work with the DC current. So, induction or some other devices based on magnetic effects, they will not work in the case of DC. They will be working fine with AC current. So, how do we represent the AC current? Small question from today's class. How do we represent AC current? The AC currents, they can be represented either with sine curve or cosine curve. So we can represent with this equation y equals to a sine x as an AC current. So we can represent the AC current with this function. So in this way, say that E would be equal to E naught sine omega t, or I can also write that current I will be equal to I naught sine omega, where I naught and E naught, they are the peak values of current and EMFs. So depending on AC, we have different devices. We call them as LCR devices. L, C, and R. L is called as an inductor. It operates very well on the AC current. C is capacitor. As you have heard about the condenser or capacitor. I hope you must have seen in your ceiling fans, there is a small device which we call as the condenser of the fan. We call it as capacitor. To operate in a DC circuit. All of them cannot operate in a DC circuit. They can operate very well in an AC circuit. L, C, and R. So this is how the AC current is in the AC current happens. Also, we learned about an important AC device, that is transformer. So let us see how the transformer works. We have an important work with the transformers. So just now we observed that there are two types of transformers we can use. We can use a step up transformer and a step down transformer. Step up and step down. So step up transformers are the transformers which are used to increase the voltage. They increase voltage. Whatever voltage is supplied to them, they increase that voltage. So increase voltage and decrease current. Whereas step down transformers, they decrease voltage. For example, just now we discussed that from the power station, the voltage that is transmitted, it is transmitted at 33 kilovolts. So from the power station, it is transmitted at 33 kilovolt. Then it is brought down to 11 kilovolts by a transformer. So see, from where it is produced to the major cities, it is transported to the major cities at 33 kilovolts. So it's transported at a very high voltage so that there will be less amount of energy losses. However, if you think of transporting DC current at 33,000 volt, so this would be a very high voltage, and such a voltage cannot be maintained. It's very difficult
Yes.
to maintain a voltage of 33,000. Okay. However, with AC, it's very simple. You generate that 33 kV, you transport that, and then wherever you transport to those cities, over there you can build your substations. Those substations will bring down that AC current to 11 kV. Then the 11 kilovolts will be down to 440, which will be transported to each house at 220. There are certain heavy industries which take use of the EMF at high voltages or current at high voltages. Like some of them they may take 33 kV, some of them they may take 11 kV as the input. Some of them may take 440 kV, 440 volt as the input. Okay. So I hope you have understood about this. Okay. Now in the representation of the AC current, as we observed here, that the AC current changes as a function of time in the form of sine wave. We can represent the AC current as a sine wave like this. So we can represent the
Yes.
AC currents like this. And this maximum value of the EMF, this maximum value of the current that is available, this maximum value is called as the peak value of current. So peak value of current. Then the value of current at different instants. Suppose I want to find out the value of current at this instant. So the value of current at this instant or at any instant will be called as the instantaneous value of current. So we
Yes.
related an equation, instantaneous value, instantaneous current. So if you observe that when you are getting the AC supply, you are not continuously getting 220 volts. Your 220 volts, what you say that 220 volts, it's not actually you are getting 220. When we say that you are getting 220 volts, so that means that 220 volts which we are getting, we call this value as the RMS value of current. This is the RMS value of current. RMS means root means square value of the current. So this is the that voltage which is equivalent to the DC voltage. While in AC, if you are getting a 220 RMS value, it means the peak value of the current will be still higher. The peak value of the voltage or the peak value of voltage, you will get something about 303 volts. If you have said that at your home you are getting 220 volts, so it means you are getting actually 303 volts as the peak value. This is the peak value, and the minimum value that you are getting is 0. So the value of EMF is changing continuously, right? So if you are touching if you are getting electrocuted, you are actually not getting a shock of 220 volts. You are getting a shock of 303 volts, but it's varying. It's not continuous. Within a second, you are getting about 50 shocks. You are getting 50 shocks per second, 50 to 100 shocks per second. Whereas
Yes.
In the DC, it's not so. If it was a DC current, so in DC current, the value of current would remain the same, or the value of voltage will remain the same. If I represent for DC current, so for DC current, it would be something like this. For DC current, again, if I plot voltage versus current, so once you switch it on, you will have this peak voltage, and after that, it will continue to remain at that voltage. If you turn that off, so you will get a voltage zero. There will not be fluctuation or variation during this time. So this will,
Yes.
you can say this is the maximum value or the peak value. This is maximum value of EMF, and this is the zero value. So either it will have two values, either it will have a maximum value or it will have the value zero of the EMF. No other values of EMF are possible. So I hope you have understood the difference between an AC current and a DC current.
Yes.
Okay, so AC currents, they are also used in transmission of electric power, transmission of electric power in the form of EM waves. As we have heard about the electromagnetic waves, so whatever radio waves and everything they are sending out, over there we find mainly use of AC currents. So that is why in our homes we have supply of AC currents. First of all, there is loss of energy is less. AC can be transported to longer distances. Okay. A number of devices can run on AC, right? Whereas with DC only a few devices can. Even if you have, if a device is running for a longer duration of time with AC, so there is no problem. But with DC, if you are continuously running a device, it will get continuously heated up, and it is likely to get a fault very soon as compared with the AC. With AC, you will be getting a fault very late, but with DC, the fault will occur very soon. Okay. Okay, so we have completed today about the topic AC or alternating currents. Right? Any doubt with the AC or alternating current? No?
No, sir.
Okay. So we'll see if our next topic, and then we can start that next topic in the next class. Let's see.
Sir, we'll start from the first chapter onwards in the almost in the first May of week of May.
Yeah, in the first week of May, we'll be starting with first chapter in detail. So
Okay.
over there, you do not have any sense of doubt or anything like. So everything will